Hi everyone, welcome to this episode of Keipert Labs. In today's video we're going to be discussing the concept of electron configuration, thinking about the structure of atoms and digging a little further into how they are put together. So the first thing that we're going to do, as ever, in our overview we're going to talk about reviewing the Bohr model and kind of thinking about the features of this model of the atom that we're working with at the moment. We're going to look at this, introduce this concept of, or revisit the concept of shells, and looking at how electrons fill up the shells in an atom, and then looking at electron configuration as a shorthand way of us representing where those electrons are. Okay, so we're thinking about the Bohr model of the atom. That's the atomic structure that we're working off from here. Okay, so where we've got the nucleus in the center, containing positively charged protons and neutral neutrons. Now this diagram is certainly not to scale, because remember the nucleus is very, very small and there's a lot of empty space. And then, aside from the nucleus in the center, we have electrons orbiting around the nucleus in shells. Okay, and so one of the features of the Bohr model, and which we'll kind of unpack a little further, is this idea that we have these defined orbits rather than just kind of randomly orbiting all in the same kind of distance. So they're kind of the two kind of key aspects of this model. And so we're looking at this idea of electron or energy shells, energy levels, electron shells. So there's kind of some synonyms used in this kind of terminology. We'll try and stick with the word shells to help us to understand. So in the Bohr model, so that he said that electrons are found in these defined orbits called shells. Now, this idea is that there's multiple shells that electrons can fit into, and the shells are given a number. Starting from the nucleus and working our way out, we talk about the first shell, the second shell, third, fourth, fifth. So, and we represent that with a lowercase n. So any number 1, n of 1 or n of 2, and that sort of thing. Okay, so we don't have an infinite number of shells, because what we remember is that even the largest elements that we know of, or we've been able to create so far, only have 118 electrons. Now, obviously, that is a lot of electrons, but we're not talking thousands here. We're talking a very specific, relatively small number. And then from the smallest elements going up, we might only have 1, 2, or 3 electrons to try and place. But this idea being that we start from the center, where these shells will be based, and then we move our way out. As that distance from the nucleus increases, as we talk about shells that are further from the nucleus, we talk about their energy level increasing. So if we take a look at this image here, that the energy level of the second shell is higher than number 1, and then it gets higher for number 3 and 4 and 5 and so on. Okay, part of the reason of that is a way to try and account for the behavior of electrons in shells that are not as close to the nucleus. If we think about them in this way, it helps to make a lot of sense about why they do what they do. Okay, all right, so that's kind of the numbering of shells. And we look at this idea that the shells have what we call a fixed capacity. And so that we can't just pack an infinite number of electrons in that based on where the shell is, that it can only fit or be allowed to contain a certain number. And as we get to bigger shells that are further from the nucleus, that we get a bigger capacity. So as we see, the first shell can only contain a maximum of 2, but the second shell can contain a maximum of 8, the third shell 18, the fourth shell 32, fifth shell bigger again, and so on. Okay, and so what we see is that there's a mathematical relationship here, that the maximum number is given by the rule of 2n squared. We're reminding you that n is that number of the shell. Okay, so for, say the shell number 2, so n equals 2, 2 times 2 squared equals 8. Okay, so it's just a way for us to be able to predict the maximum number of electrons that we can fit. Now, we may not need to fit all of those electrons in the shell. Depends on how many we have to try and find space for. Okay, but that's the maximum. Once we reach that, then we have to continue on to the next shell. Okay, so now we'll have a look at, walk you through how this might look. Okay, so the idea being, I was saying, the maximum number of electrons we can fit means that once that shell becomes full, we have to start filling the next shell, the next available, the next lowest. So we kind of go up to the up one. So if we have a look at representing the shells for helium, which is atomic number 2, and then going to lithium, which is atomic number 3. Now, if you happen to have a periodic table handy, or you can pause for a moment to have a look for one, you can see that helium and lithium are on opposite sides of the periodic table. Helium is in the far top right-hand corner, and then lithium, even though it's only one atomic number up, is all the way back over onto the left. And here's a little bit of an insight into why. So for helium, which has 2 electrons, because atomic number 2, then we place those 2 electrons into that first shell. But remember that that first shell has a maximum number of electrons of 2. So even though that's how many we've added, we've now filled it up. So that means that if we go to 1 more electron in the case of lithium, we have to then place that into the next shell. So we have 2 in the first one and then 1 in the second shell. So 3 altogether. And we see the same sort of idea as we go, if we kind of bump it up a little bit, as we go from neon to sodium. So neon has an atomic number of 10, which means 10 electrons. So we place 2 in that first shell, and then we've got 8 more to place. So we go 1, 2, 3, 4, 5, 6, 7, 8. Now the fact that I've paired them up over here is not something we're going to discuss about now, but it does have relevance for what's going to come a bit later. So I've filled in all of these 10 electrons, but remember from the previous slide that that second shell is now full. It is complete, because we can only have a maximum of 8. So if we go to sodium, which is atomic number 11, so 1 extra electron, we have to go to the next shell. So now we have 3 shells. We have 2 in the middle, then 8, and then we've got 1 electron. Now, just a kind of a quick kind of touch on it, but not something we're going to go into in much detail, is that you notice that so that on the periodic table, lithium and sodium are directly underneath each other, and they both have 1 electron in this outside ring. Okay, now it's not the same shell for each of these ones, but both of them have only 1 thing on the outside. Okay, but that's for another video. And so now we're going to say, all right, well, this is how we've drawn it. You know, we've gone to this effort to actually show where the electrons are and which shell they're in. But is there a simpler way that we can represent this arrangement without having to draw it out all of the time? And the answer is yes, that we have what we call the electron configuration. So which is a shorthand notation of how many electrons are in each shell. So it's a shorthand, it's a quick number representation that gives us the same information once we're a bit more familiar with how to read it. So if I show you, and it involves numbers and commas, okay, that's really as complicated as it gets. So I'll show you a bit of how that works, and then you're going to have a practice with some different ones. Okay, so if we bring up the same electron arrangements of helium and lithium that we had before, so what we can say is, all right, helium's got 2 electrons. Okay, and so what we do is we give it the number 2. We have 2 electrons in the first shell. So we give it a number 2. I've just done it red here to stand out, but it's not a color thing otherwise. Now for lithium, like I said, we've got 3 altogether, but we've got 2 in the first shell and 1 in the next one. So what we do is we write that as 2, 1. So 2 in the first and 1 in the second shell. So now we go to the next one where we've got neon and sodium. Okay, so notice we've got 2 in the first shell and then 8 in the second one. So we call it 2, 8. And then now remember, because we added that extra shell for sodium, we have 2, 8, and 1. And so now we write it like this. So you can see that as you get a bit more practice with how to actually connect these 2 concepts together, that I can say, all right, well, sodium's got 2, 8, and 1. And you're like, oh, okay, yep, I get that. And then you can draw it out. And likewise, you could be presented with a diagram and be able to translate that across. The reason for that is that it helps us to be able to describe where these electrons are in a simple and quick way. Okay, so just to recap, we reviewed some of the key ideas of the Bohr model, the idea of the nucleus in the center and electrons orbiting around the outside in shells. We described what we mean by the shells, and they have this number, 1, 2, 3, etc., and that these shells are where we place the electrons, that they have a fixed capacity, that when we fill them up, it's given by the mathematical relationship of 2n squared, 2 times the number of the shell squared. And that we can use electron configuration as a shorthand way to represent where those electrons are. All right, thanks very much for watching. Bye for now.